Hello and welcome to this section of the Calculus 1 Derivative Tutor. In this section we're going to learn about how to take derivatives of functions that involve the natural logarithm. That's the LN button on your calculator there. So we'll give you a little bit of a review about what a natural log is, and then we'll teach you how to take a derivative of that guy, and then we'll do a lot of problems to show you how to do that when the functions get more and more complicated. So what you're going to find is that up until now, all of the rules of differentiation that you have learned really enable you to take derivatives of almost any function you can think of. Definitely algebraic functions, radicals, powers with exponents in there, even fractional exponents, negative exponents. You can do a lot of things. You know the trigonometric derivative, so you can use that in concert with the chain rule and other things to do really complicated, taking derivative of really complicated functions. But as you go up and up in math, some additional functions pop up more than others, and so we're going to learn how to take the derivative of those. Obviously, the trig functions pop up all the time in science and engineering, so we have learned how to take the derivative of that. Another guy that pops up all the time in science and engineering is the natural log. Now, don't forget, when we say natural log, it's just a regular logarithm like you've learned about in algebra with a base, instead of a base 10, like a regular log log that you might see on your calculator, instead of a base 10, a natural logarithm is base e, where e is that special number 2.71 and then a lot of decimals after that. E pops up all over in nature. It's something you'll find in almost every science class from here on out. E and pi are just best friends, and e and pi pop up all the time. Of course, pi is a lot more famous than e, but the natural number e pops up all the time. So what we want to do is recall what this guy is before we learn how to take the derivative of it. Recall the natural log. Okay, so we sort of talked about it, but just to drill it home, basically there should be a button on your calculator with ln. It might be a second function somewhere, but you'll see ln of x. That means, basically, if you see ln of x, what it really means is it's the regular logarithm like you've learned about before, but instead of a base 10 here, which is typically what log is referencing, base 10, it's base e. So when you see natural log of x, is how you would say it, natural log of x, it's just a regular logarithm with a base e of x. And what this really means, when you have a natural log of anything, is, just to kind of make it clear, it's base e, which I've denoted here. And what it basically means is if I have the natural log of a number, I put a number in the calculator and hit the natural log button. Basically what the calculator is trying to do is it's trying to take the base that's implied here, that's an e right here. It's taking that base, it's trying to raise it to some power that it's trying to calculate so that the answer will be x that I put into my calculator. So whenever I take, 3, and I press the natural log button, the calculator's going through and iterating through some calculations, and it's trying to find an exponent such that e raised to the power of whatever exponent I find as the answer is going to give me the number that I put in there. So what the natural log is really doing is finding this exponent. That's what it's doing. It's taking the base, finding some exponent that will equal whatever it is you typed into it, and that's what the natural log is doing. I could go on and on as to why it's useful. What you're going to find is that as you finish through calculus 1 and 2 and 3 and you go on into differential equations and you go into physics and engineering, you're just going to find that this base e here, this number e, is very, very special, just like pi. So this natural log function, which involves base e, pops up a lot. It definitely pops up in advanced calculus all the time. And so you're going to find, in other words, what I'm trying to say here is don't blow this off as like, well, I'll never use natural log. I'm just going to kind of fast forward through this part. You're going to use natural logs all the time. So it's important to know how to take the derivative. Now, the good news is it's extremely simple to take the derivative of this guy. And I'm just going to write it down and we'll talk about it a little bit. The derivative of the natural log function, ln of x, is simply equal to 1 over x. And that's it. And there's no proof here. I haven't proved anything to you. I'm not going to try to prove anything to you. What you're going to find when you study this in your calculus class is your book will make an attempt to give you some sort of proof. I could try to go into that, but to be honest with you, it involves some topics that we haven't discussed yet, and it's honestly not that important. I'm not going to sit here and say that not understanding where things come from is a good idea. You should always try to understand where things come from. But ultimately, just like I told you, hey, derivative sine is cosine. Derivative cosine is negative sine. I really didn't try to prove that to you. My job is to sort of tell you what is fact and give you the skills to do well and to sort of build your knowledge, right? And the book's job and your professor's job, I think, is maybe dig a little deeper with that for those of you who want to go a little deeper. But ultimately, all you really need to know is if you see a natural log of x and you take its derivative, the answer is always going to be 1 over x. Always, always, always. So that's basically it. That's how you take that. It's no more difficult than that. Now what we're going to do now is work some examples that involve natural log function that are a little bit more complicated, and we'll learn how to do that. So this is what you need to take away from this lesson. Now let's do a practical problem, something you might actually see. Let's say you have a function f of x, and it's equal to the natural log of x plus 1. Now you see what I've done here. It's a little bit of a bait and switch. I told you, well, derivative of natural log is 1 over x, and the problem I'm giving you here is not really the same, obviously, because this is just so darn easy. I mean, anybody could just spit this out. But what do you do with this? This is a little bit different, because I have a natural log which matches this, but instead of natural log of x, it's natural log of something more complicated, x plus 1. Well, here's where your mind should expand a little bit in calculus. Just like we did it with the trigonometric functions, we're going to do it here. We basically have a nested function here. So we're going to use the chain rule as the answer to the question. So you have an outer function. The outer function is the natural log, is sort of the largest thing here. On the inside, we have this inner function. So ultimately, all we have to do to find the answer here is use the chain rule. So the derivative of this function, you just take the natural log, the derivative of the natural log, as it stands with the argument that it has. So since the derivative of this is 1 over x, derivative of this would be 1 over x plus 1. Now, a lot of students would just stop there and say, well, I found the answer. But you should know now from the chain rule that you can't stop there because you have a nested function. So you have to multiply by the derivative of the inside. The derivative of x is just 1. The derivative of this is 0. So in this particular case, the answer really is 1 over x plus 1. And that's the answer. But I think you can see that if this were anything more complicated on the inside, the answer would not be so simple. We'd have some terms multiplied out here, which would be the derivative of the inside. This is exactly the same as when we did trigonometric stuff. Derivative of sine is cosine. But if you have sine of x squared, then you take the derivative of the sine and then you multiply by the derivative of the inside. It's exactly the same thing here. We have another function. Instead of a sine, it's a natural log. But it's exactly the same process. So when I say, I hope it opens your mind, I really mean that. It's because hopefully by now you'll start to see the patterns that once you learn the fundamental ways to take derivatives, chain rule for instance, how to apply the chain rule, then it doesn't matter if you've got a natural log or a sinusoid or later on maybe a hyperbolic function like sine h or any other function you want. Once you know how to apply the chain rule, you will know how to do it. At least from a big picture point of view. Take the derivative of the outside, multiply by the derivative of the inside, and you just keep going in and in and in until you're done. So let's get a little more practice with this. Let's say we have f of x is equal to x times the natural log of x squared minus 1. Now this is a little more complicated, obviously. But you can see from a large picture you have a function multiplied by another function. Right, so this is sort of a function here, this is another function over here. So you have two things multiplied together. So we're going to need to use the product rule. Right, so let's write the product rule out and see where that takes us. So the derivative of this function is first times derivative of the second plus the second times the derivative of the first. So it's the first times, and just to make it clear, we'll just write it like this. The derivative of the second plus the second function times the derivative of the first function. Now, as you get a little more experience, you could skip steps a little bit here and take these derivatives, as you write it out, but it's more clear here because then we just go to the next step and we look here and we say, okay, I have to take the derivative of this natural log function, which is basically just like we did here. It's exactly the same thing here, except the inside is a little more difficult. What is the derivative of the natural log itself? This is 1 over the argument, x squared minus 1. We can't stop there. We have to multiply by the derivative of the inside, which is just 2x. Because the derivative of this is 2x, so the derivative of this is 0. So that takes care of this derivative. Now over here, we have the natural log of x squared minus 1, and the derivative of this x is just 1. Okay? So basically our derivative's done. This is the answer, but let's simplify it a little bit. So f prime of x is equal to 2x squared. This is all multiplied together, so we have 2x squared over x squared minus 1, that's this whole term, plus natural log of x squared minus 1. So I have 2x squared over x squared minus 1 plus natural log x squared minus 1. That's the answer. So that's what you would circle on your test. So you see, the process that we are following here is exactly the same process that we've used for everything up until this point. You look at what you have, you apply the rules of calculus in a logical manner. You see that you have two things multiplied together, so the largest thing that we need to deal with is the fact that these things are multiplied. So we do first times derivative of the second plus the second times derivative of the first. Once we get to a derivative that involves a logarithm, we apply what we've just learned today, but we know we have to use the chain rule because inside here is more complicated than a simple x. So we do that, and then we just basically collect terms. And that's all that's going to happen in the remainder of these problems. It's just that we're going to get a little more practice as we go along with a little bit more complicated functions. So f of x, let's say you were given the natural log of the square root of x minus 3 over x minus 2, right? So that looks really complicated. The first thing I always recommend is for people to write this in terms of an exponential. So instead of with a radical here, x minus 3, let's write it as x minus 2, and let's write it to the 1/2. Right? So we've been doing that consistently throughout the entire course, so it shouldn't really surprise you. I just like doing that because you'll see later, ultimately, we're going to use this 1/2 all the time as we take the derivative. So the derivative, first derivative, is the largest thing we have to deal with is the fact that we have a logarithm here. Everything on the inside comes later. We're going to deal with that later. So first we just have 1 over everything on the inside. So we have x minus 3, x minus 2, and we have 1/2. So that's kind of ugly looking. We'll get to simplifying that later. We can't stop there. We need to multiply by the derivative of the inside, but this inside term is quite ugly. You see on the inside we have a quotient here, but we also have the entire thing raised to a power. So sort of the largest thing inside of here is going to be dealing with this power first, and we've been doing problems like that. So multiplying by the derivative of the inside is going to be 1/2 x minus 3 x minus 2, subtract 1 off the exponent, negative 1/2, but we can't stop there because we've just done sort of in the inner layer, we're peeling back the onion. We have 1/2 times this times to the negative 1/2, but we have to multiply by the derivative of the inside of this term. So I'm going to put a big dot here because we're going to be multiplying this whole expression by the derivative of the inside here. So you see we're using the chain rule going in, continuing to multiply, taking the derivative as we go. How do you take the derivative of these two things multiplied together? Easiest way is to use the quotient rule. So we say bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Now at this point you might be looking at this saying, well, this is really ugly, I'm definitely on the wrong track. A lot of times on tests you get concerned, but everything is absolutely legal. We turn this over into an exponent here instead of the radical. We take the derivative as 1 over this guy, that takes care of the logarithm, and then we multiply by the derivative of the inside. The outermost thing we have to deal with here is the 1/2, so we do it just like we use the chain rule, 1/2 times the inside to the negative 1/2. Then we multiply by the derivative of the inside, which happens to follow the quotient rule. Now we're done. We can't go in any deeper because we've done everything we can. So now it's just a matter of simplifying. So f prime of x is equal to, let's look at what we have, just to make ourselves a little bit more sane here. We have a 1/2 right? And we have this guy to the negative 1/2. So let me move this downstairs because this is looking exactly like this. Once I move it downstairs and make this positive, I'll have these two guys here, and then I will have the 1/2. So let me go and put 1 over. The 2 from the 1/2 comes out, and then I'm going to have x minus 3 over x minus 2. And I'm just going to put it to the 1 power because basically what happens is I take this and I move it downstairs. It's multiplied by this term, so 1/2 plus 1/2 from here is going to give me 1. So I've added those together right there. Then, to continue on with the derivative part, I still need to work with this. So I've got x minus 2. The derivative of this term is just 1 because the derivative of this is 1. Minus x minus 3. The derivative of this is just 1. So I write this. And then on the bottom, I've got x minus 2 squared. Now I've taken the derivative, so effectively I'm really done with the problem. Let's go ahead and try to simplify this a little bit more. Now this is not a prime, this is just the first power. I just wanted to make it clear what I was doing there. So f prime of x, let's for now keep it as 1 over, actually, you know what, let's go ahead and do it this way. This is a 1 over this giant fraction, so let's go ahead and flip it over and make it x minus 2 on the top and 2 times x minus 3. All I'm doing in this step, since I've got 1 over this fraction, is I'm flipping this fraction over. The 2 stays down there. Nothing happens to the 2. These guys flip around. All right, now in here, what I'm going to have is let's go and distribute these negative signs here. So it's x minus 2 on the top minus x plus 3, distributing this guy in, and on the bottom I'll have x minus 2 squared. Okay, so I think you can see where we're going here. We have x and we have minus x, so that's going to cancel. And now I have x minus 2 here, and I have x minus 2 squared there, so this is going to disappear. This exponent's going to disappear, leaving me with one of these on the bottom. So the final answer, f prime of x, is equal to. The only thing I have on the top is negative 2 plus 3, so I have 1 on the top. On the bottom I have a 2, I have an x minus 3 from here, and I have an x minus 2. And that, my friends, is the final answer. 1 over 2, x minus 3, x minus 2. Now, truthfully, this really is the answer as well. It's just a matter of simplifying here. You got to peel back the onion. First we deal with the logarithm, then we deal with the fact that we have this raised to an exponent, then we deal with the fact that we have this guy as a quotient on the inside. The rest of it is just algebra, simplifying it down to a form that looks a little bit nicer. So that's sort of the deal. You know, people look at the derivative of natural log and they're like, oh, I got it, piece of cake, just 1 over x. But you really do have to practice integrating that natural log with other functions so you can kind of get comfortable how to handle it. All right, so let's say you had f of x is equal to the natural log of x over 1 minus x. And we want to take the derivative of this guy. Well, the first thing I notice is, yeah, I've got a natural log, but bigger picture than that, I've got a giant quotient. I've got this guy on the top, you know, if you think about it like this, and I've got this guy on the bottom. So I do need to follow the quotient rule. So that's what I'm going to do. F prime of x is equal to the bottom, 1 minus x, times the derivative of the top, natural log of x prime for a derivative. Bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared, 1 minus x squared. All right, we haven't taken any derivatives yet, so let's go and do that now. F prime of x is equal to 1 minus x. What is the derivative of natural log of x? Well, we talked about it. That's the whole point of this section. That's 1 over x minus natural log of x. What is the derivative of this term? Well, this is derivative is 0. This derivative is negative 1, because that's what's sitting out in front of the x, all over this guy, 1 minus x squared. Okay? So, what we're going to do next is distribute this 1 over x in, because this is really the answer. But let's try to simplify it a little bit better if we can. Okay, so the next thing we're going to do is multiply this guy in. So we'll have 1 over x minus 1, because this times this, the x's will cancel. Minus comes from here. Minus, well actually plus, because negative times negative is positive, natural log of x over. And the bottom is 1 minus x squared. Now this really is the answer. You can circle this on your test, but just to make things a little bit more interesting, let's try to simplify this a little bit more. Let's pull out a 1 over x on the outside on the top. On the inside, we'll have 1 minus, and then we'll have an x here, plus, and then we'll have an x here, natural log of x. Notice what I'm doing. If you back distribute this back in, you'll have a 1 over x here, you'll have minus 1 here, and you'll have natural log of x here. On the bottom, you'll just have the 1 minus x squared. Why am I doing that? Because if I do this, then the final answer can be written as, this is 1 over x on the top, I can move it to the bottom. So on the top, I'll just have 1 minus x plus x times natural log of x over, this x comes down, x, 1 minus x squared. And that's the answer. So I have 1 minus x plus x natural log of x over x times 1 minus x squared. Now again, you really could leave the answer like this. The only thing that's ugly about it is you have this fractional x on the top. So really it's just a matter of style. I pull it out so that I can stick it on the bottom basically, and I don't have any ugly fractions anywhere. I just have x's everywhere. But really and truly, that's just totally subjective. I mean, you could leave it like this. If you're really crunched on a test, you could even leave it like this because that's just a simplification. So we're plowing through these guys. I have a couple more to show you, but I hope that up until this point you can see that knowing that the natural log of x, that its derivative is 1 over x, is really important and seems really simple, but as you apply it to problems, you really do need to get a little practice integrating it into a quotient or into a product rule or into a chain rule. Once you get that guy down, then all of these problems are going to be quite simple. So the next problem is f of t, some function of time, let's say, is the sine of the natural log of t. So here we've got a sinusoid interacting with a natural log. But ultimately, you've got to look at the big picture first. I've got the sine outer function. The inner function is the natural log. So I need to use the chain rule, right? So we've done a lot of practice with this before, but now we're integrating the natural log into the mix. What is the derivative of sine? It's cosine. So you leave the argument the same because you take the outer derivative first. Then you multiply by the derivative of the inside. The derivative of natural log is just simply 1 over the variable. So ultimately, your final answer is going to be quite simple. Cosine of natural log of t over t. So I just take this t and I bring it down below. That's the final answer. Very simple problem, but I want to just show you how it can interact with a sinusoid there when you're doing your problem. So final problem, let's go f of x is equal to the natural log of x. So here I have two natural logs. One is nested inside of the other, but exactly the same thing holds. You have an outer function, that's this natural log. The inner function is also a natural log. But you don't do anything crazy, you follow exactly the same rules. F prime of x is equal to. Well, the derivative of this outer function is what? It's 1 over the argument. So this natural log of x has to go in the bottom because it's 1 over whatever's on the inside. But then you multiply by the derivative of the inside. The derivative of natural log of x is 1 over x. So ultimately, the final answer is 1 over x times natural log of x. And that is the final answer. Well, that about does it for dealing with derivatives that involve the natural log function. Natural log pops up in all levels of science, mathematics, engineering. It doesn't seem like you may have used it too much prior to calculus, in like a high school algebra class or something like that. That's just because really they pop up in real-life applications of things that you usually study when you get into some more advanced classes. But you're going to have to trust me here. The number e, which is the base of the natural log function, super important, pops up in all levels of science and engineering and mathematics. And the natural log function, since it involves that base number, e, pops up all the time as well. So taking the derivative of natural log is going to be just as important as taking the derivative of any other function that we've studied up until this point. All right, now one thing I'll say is we've talked about how to take the derivative of the natural log function. That's with base e. In the next section, we're going to learn an equally important thing. We're going to learn how to take the derivative of an exponential e, base e, raised to the power of x, e to the x. That's equally important. So this section and the next section kind of go hand in hand because e is tied together at the hip with the natural log function. So knowing how to take the derivative of both of those guys is very, very important.